In previous videos, I've talked about the geometric definition of the dot product, and in this video I'm going to go over a different definition, which is the component definition, or sometimes called the coordinate definition. And to do this, I'm going to multiply out two vectors symbolically, so I've got A and B, which are three-dimensional vectors written in their unit vector form, where we've got an x, y, z axis with their x, y, and z components. And so let's multiply this out. So we're just going to multiply each term with each other. And I'm going to multiply this term with this term and bring the components out in front because they're just scalar values. And then it looks like this. You got your I hat, dot I hat, and we're going to do that for each term. So AX, BY, then I dot J, and then AX, BZ, I dot K, and we're going to do that for every term. So AY, BX, J dot I, plus AY, BY, J dot J, plus AY, BZ, J dot K. Sometimes it takes a while to write everything out. AZ, BX, K dot I, plus AZ, BY, K dot J, and then finally AZ, BZ, K dot K. So now we have this long, ugly multiplication. Let's see what we can do to reduce this. And we're going to look at the properties of the dot product once again. So if I draw out three-dimension coordinate system, and you have I, J, and K, recall that the dot product is, in our geometric definition, is this. A dot, or A magnitude, B magnitude, cosine theta. And so the properties of cosine is when cos is 90 degrees, it's 0. And when cosine is 0, it equals 1. So we can reduce this by looking at, since all these vectors are either 90 degrees from each other or 0 degrees from each other, we can look at this equation and reduce the terms and come up with some properties. So I dot I, J dot J, and K dot K are all in the same direction, which means they're 0 degrees from each other, and so these terms are 1. So I dot I equals J dot J equals K dot K is equal to 1. So that reduces that, but look at these other terms, I dot J, I dot K. All these terms are 90 degrees from each other, and so therefore they equal 0. So any term that has values, I, J, or K, that are different from each other, like so or like this, etc., equals 0. And so that can reduce a lot here. That means I dot J, this term 0, I dot K, this term is 0, J dot I 0, J dot K 0, K dot I 0, and K dot J 0. The rest here, this is 1, this is 1, and this is 1. And so if we write that out, we're left with AX, BX plus AY, BY plus AZ, BZ with no vector values. So our vectors are gone and we're left with a scalar value, which is what we'd expect to see. And so this is our new definition of the dot product, and it's only in the form of the components. So let's look at two vectors. If we have a vector A and a vector B, what we're essentially doing is we can draw out its components, and I'm only looking in 2 dimensions here now. So you can pretend there's no Z term here. We've got our AX, BX, AY, BY, and you're just multiplying your similar components with each other and then adding the multiplication of the other two components. And so that is basically it for this definition. It's probably an easier definition um, to work with because we know how to find vector components now, and all you have to do is add the product of the components, and you have your dot product. No angles or anything involved in this, just the components. And so that is that is the component definition, and we'll do some examples with it in the following videos. Thanks for watching.